You are standing on a plain of frozen nitrogen, 5 billion kilometers from home, and above your head a thin blue mist is quietly moving across a black sky. That mist belongs to Pluto, a tiny frozen world so far away that most people forgot it was even still out there. Scientists just discovered that this thin blue haze might be steering the entire climate of a whole world and quietly stealing pieces of its air into space forever. And that changes what we thought we knew about small, cold places. Stick around and tap that subscribe button right now, because by the end of this video, you will understand a secret about tiny worlds that most planetary scientists only figured out in the last few years. Pluto is not supposed to matter this much. It is smaller than our own moon. It sits so far from the sun that daylight there looks like a deep twilight back on Earth. For a long time, most people treated it like a leftover, a rock too small and too far to bother studying closely. But something has been happening in Pluto's sky for billions of years, quietly, without anyone on Earth noticing. A haze made of tiny particles, thinner than smoke, has been drifting far above its icy ground. And in the last few years, a giant telescope pointed straight at it and found something nobody expected. What that telescope found is not just a fact about a distant rock. It is a clue about how any small world, anywhere, might hold on to its air, lose its air, or quietly shape its own weather using nothing but a whisper of dust in the sky. And it starts with a question almost nobody thought to ask until very recently. Why does Pluto still have any air at all? Let us pull back now, before this becomes about telescopes and chemistry, because it begins with something much simpler. For decades, the assumption among most scientists, and most of the public who thought about Pluto at all, was simple. Pluto is small, Pluto is cold, and small, cold worlds are boring. They do not have weather. They do not have complicated skies. They just sit there, frozen and still, waiting for nothing. That is the picture most people carried around in their heads, a dead little snowball at the edge of the solar system. Keep that picture in mind, because we are about to take it apart, piece by piece. Pluto was discovered in 1930 by a young man named Clyde Tombaugh, working at an observatory in Arizona, comparing photographs of the night sky taken days apart, looking for anything that moved. He found a tiny speck of light that shifted position against the background stars. That speck became Pluto. Think about how strange that is. A world was found not by seeing it clearly, but by noticing a single dot that quietly refused to stay still. Everything we know about Pluto today grew out of that one small, patient act of noticing. For decades after that, Pluto sat in textbooks as little more than a name and a dot on a diagram. Kids memorized it as the 9th planet. Nobody could describe what its surface looked like, what its sky looked like, or whether it even had a sky worth describing at all. For most of the 20th century, Pluto stayed a mystery. It was too small, too dim, and too far away for even the best telescopes on Earth to see clearly. Astronomers could barely tell it was round. They guessed at its size. They argued about whether it even had an atmosphere, that thin layer of gas that wraps around a planet or moon and can carry weather, clouds, or wind. Then, in 2015, everything changed. A spacecraft called New Horizons, after a 9-year journey across the solar system, flew past Pluto for the first time in human history. It carried cameras and instruments built to answer questions nobody could answer from Earth. What New Horizons found stunned almost everyone watching. Pluto was not a dead, frozen ball. It had mountains made of water ice, some as tall as the Rockies. It had smooth plains of frozen nitrogen that looked freshly resurfaced, like wet sand at low tide. It had glaciers slowly flowing, the way ice rivers flow on Earth. And high above all of that, wrapped around the whole tiny world, it had a thin, hazy atmosphere, layered like blue gauze, stretching hundreds of kilometers into space. That haze surprised everyone. Nobody expected a world this small and this cold to hold on to any real atmosphere, let alone one with visible structure, layers stacked on top of each other like a wedding cake made of mist. Here is why that mattered so much. An atmosphere needs gravity to hold it in place. Pluto's gravity is weak, roughly 1/17 of what you feel standing on Earth. A world with gravity that weak should struggle to keep gas from leaking away into space. Yet there it was, a hazy, layered atmosphere, somehow surviving at the very edge of our solar system. Scientists began measuring what that atmosphere was made of. It turned out to be mostly nitrogen, the same gas that makes up most of the air you are breathing right now, mixed with small amounts of methane, a simple gas made of carbon and hydrogen that is also the main ingredient in natural gas here on Earth. Sunlight, even the pale, weak sunlight that reaches Pluto, can break methane molecules apart. Those broken pieces then stick back together into new molecules, and over time, some of those molecules clump into tiny particles. Those particles are the haze. Picture smoke, so thin you could barely see it if you scooped up a jar of Pluto's air, drifting upward, layer after layer, into a sky lit by a sun that looks like just a very bright star. Stand on Pluto's surface for a moment in your imagination. The ground under your boots would crunch like packed snow, made of frozen nitrogen instead of water. The air, thin as it is, would still carry that faint blue haze overhead, scattering just enough light to paint the horizon in soft, dim color, even though noon on Pluto looks more like dusk back home. It is a strange kind of beauty, quiet and cold, built entirely out of chemistry happening far too slowly and far too faintly for any human eye standing there to ever notice it changing in real time. By the time New Horizons finished its flyby and sent its final pictures back to Earth, scientists had a clear working theory. Pluto had an atmosphere. That atmosphere had haze, and the haze was probably just a strange decoration, a side effect of chemistry, floating above the real action happening down on the icy surface. That became the story most people settled into. Pluto has ice mountains and frozen plains and glaciers, and yes, some haze up above, but the haze is basically scenery. The real geology, the real drama, is on the ground. The sky is just where old gas goes to die before it eventually escapes. News articles at the time leaned into this framing too. Headlines celebrated the mountains, the glaciers, the surprisingly young-looking plains, because those were the images people could look at and immediately understand. A grainy infrared measurement of atmospheric haze does not make for nearly as dramatic a photograph, so it slipped quietly into the background of the story, mentioned but rarely explored. Even among planetary scientists, attention naturally drifted toward the surface features first. Mountains and glaciers fit neatly into categories geologists already understood from studying Earth and other planets. A thin, structured haze layer, doing something nobody had ever documented before on a world this small, did not fit any existing category quite as easily. Every instrument on New Horizons had been built and tested for nearly a decade before that flyby ever happened, engineers double-checking cameras and sensors that would only get one single chance, a few short hours, to gather data on a world nobody had ever seen up close. There was no second attempt possible. If something had gone wrong during those few hours in July of 2015, humanity might have waited another generation for another shot. Researchers noticed something puzzling buried inside the New Horizons data, though. Pluto's atmosphere was losing gas into space far faster than anyone expected for a world with such weak gravity. Something was giving those gas molecules enough energy to break free and drift off into the dark. Nobody could fully explain what. For years, that question sat mostly unanswered, an unfinished thread in an otherwise incredible discovery. Pluto had a beautiful, layered sky. Pluto was losing gas too quickly. Most people assumed the two facts were simply separate curiosities, two odd details in a very odd little world. But that picture was about to change, in a way nobody at the time predicted. A young researcher was about to look at Pluto's haze not as scenery, but as an engine, something that might be quietly running the whole show. And what came next would take years, one bold guess, and one enormous telescope to finally prove. Write in the comments the exact moment when something you believed turned out to be only part of the story, because your answers are shaping the next video on this channel. Months after the New Horizons flyby, a planetary scientist named Shi Zhang, working at the University of California, Santa Cruz, started digging into the mystery of Pluto's leaking atmosphere. Zhang was not satisfied with treating the haze as background decoration. Zhang had an idea that felt strange even to him. What if the haze was not just floating passively in Pluto's sky? What if the haze itself was actively controlling the temperature of the entire atmosphere, heating it in some places, cooling it in others, and in the process giving gas molecules the extra push they needed to escape into space? Picture a house with a very thin, wispy curtain hanging in a window. You would not expect that curtain to control the temperature of the whole house, but Zhang was proposing something like that. He suspected Pluto's haze, thinner than any curtain, thinner than smoke, was somehow steering the temperature of an entire world. In 2017, Zhang and his colleagues published this idea. Their theory made one very specific, very testable prediction. If the haze was truly cooling Pluto's atmosphere the way they suspected, It should be glowing faintly in a very particular kind of light, called mid-infrared radiation, a wavelength of light our eyes cannot see, but instruments built for it can detect clearly. Zhang later admitted that many of his fellow scientists were skeptical. It sounded almost too simple. A layer of near-invisible dust, somehow running the energy balance of an entire planet's atmosphere. Some colleagues quietly doubted it. Zhang himself called it a crazy idea at the time. Most researchers at that point expected the haze to be a minor detail, worth a footnote at best. What Zhang was proposing instead was that this footnote might actually be the main character of the entire story, the hidden engine quietly running underneath everything else scientists had already photographed and mapped. That gap, between a footnote and a main character, is exactly the kind of gap that makes a scientist's career, if the prediction ever gets tested. There was one enormous problem standing between Zhang's prediction and any real proof. No telescope that existed in 2017 was powerful enough, or precise enough, to separate that faint infrared glow of Pluto's haze from the glow of its huge neighboring moon, Charon, which sits so close by that the two worlds' light signals blur together from Earth's point of view. So the prediction sat there, published, specific, testable, and completely unconfirmed, waiting for a telescope that did not yet exist. That telescope launched into space on Christmas Day in 2021. It was called the James Webb Space Telescope, built to see the universe in infrared light with a level of detail no instrument before it had ever managed. Once it reached its position, nearly 1 million miles from Earth, and its mirrors finished unfolding and cooling to the right temperature, scientists finally had a tool sharp enough to try Zhang's 5-year-old prediction. In 2022, astronomers pointed the James Webb Space Telescope directly at the Pluto and Charon system. For the very first time, its instruments were precise enough to tell the two worlds' faint infrared signals apart. Pluto's glow could finally be studied on its own, cleanly separated from its huge neighbor. Researcher Tanguy Bertrand, who worked with Zhang analyzing the new data, later described the earlier problem simply. Before this telescope, scientists could not tell how much of the signal was coming from Charon and how much was coming from Pluto's haze, because the two blurred together from every angle available at the time. Now, with clean data finally in hand, the team searched for the exact signature Zhang had predicted 5 years earlier. A faint, specific glow of mid-infrared light coming from high in Pluto's atmosphere, exactly where the haze particles drift. They expected, at best, a rough hint that the theory might be pointing in the right direction, maybe a smudge of a signal buried under noise, something to argue about at a conference. What the data actually showed was a clear, unmistakable match to the specific glow Zhang's team had predicted years before, almost like finding the exact fingerprint you guessed would be at a crime scene, sitting there in plain sight, sharp and undeniable. Compare it to guessing, years in advance, the exact combination to a locked door you have never even seen, and then finally being handed the key, only to watch it turn on the very first try. That is roughly how confident and how surprised researchers on the team felt when the numbers lined up. Zhang later said that in his entire career studying planets, it was unusual to see a hypothesis confirmed so cleanly and so quickly within just a handful of years of publishing it. Most predictions in planetary science take decades to test, if they ever get tested at all. The haze really was doing exactly what Zhang suspected. High above Pluto's frozen ground, those tiny particles were absorbing the little sunlight that reaches this distant world, and then releasing that energy back out as infrared light, cooling the atmosphere around them the way opening a window releases built-up heat from a room. Soon after that discovery, the team dug even deeper into what this cooling effect actually meant for Pluto as a whole. And here, the story gets stranger, because a cooling haze does not just sit quietly, doing nothing. It changes everything happening around it. By absorbing the sun's weak ultraviolet light, that same thin haze was also heating certain gas molecules just enough to give them the extra energy needed to break free of Pluto's weak gravity and drift off into space forever. The very same particles cooling one part of the atmosphere were energizing gas escape in another part, almost like a single machine somehow performing two opposite jobs at once. In parallel with this work, planetary scientist Will Grundy, at the Lowell Observatory in Arizona, had already used earlier New Horizons measurements to calculate just how much gas Pluto was actually losing. His numbers showed Pluto's atmosphere leaking roughly 1.3 kilograms of methane, close to 3 pounds, into space every single second. That number sounds small on its own, spread across the surface of an entire world, but multiplied across years, decades, and the billions of years Pluto has existed, it adds up to an atmosphere that has been slowly, steadily bleeding away this whole time, kept alive only because something keeps feeding it. Here is where the story turns from strange to almost eerie. Grundy's team found that roughly 2.5% of that escaping methane does not simply vanish into empty space. Instead, it drifts across the gap between Pluto and its huge companion moon, Charon, and settles onto Charon's surface. Once that captured gas lands on Charon, sunlight and radiation slowly transform it into darker, reddish organic material, chemical compounds built from carbon, similar in spirit to the tars and resins you might find here on Earth. That reddish material has been quietly building up at Charon's poles, staining them a rusty color visible even from a telescope near Earth. Nowhere else in our entire solar system do astronomers see one world's leaking atmosphere directly feeding and physically staining the surface of its neighboring moon. Two frozen, distant bodies, locked in a slow, one-directional exchange of air and color, running for longer than human civilization has existed. Most people, hearing about Pluto and Charon for the first time, imagine two separate, unrelated worlds simply orbiting near each other, the way two neighbors might live on the same street without ever really interacting. What researchers actually found was closer to two worlds locked in a slow, quiet exchange, one very gradually breathing its air onto the other, one molecule at a time, across a gap of nearly 20,000 kilometers. Zoom out for a second and picture the two of them together, tumbling through the dark at the edge of our solar system, locked so tightly by gravity that they always show each other the same face, the way our own moon always shows Earth the same side. Now zoom back in, down to a single reddish stain forming molecule by molecule on Charon's pole, and you start to feel the strange scale this story keeps swinging between. It is worth pausing here, honestly, because even the scientists closest to this discovery admit they do not have every piece figured out yet. Whether Pluto's haze particles end up cooling the atmosphere more or heating it more depends on details still being studied, including the exact size, shape, and chemical makeup of the individual haze particles themselves, which vary in ways researchers are still trying to fully map. That admitted uncertainty does not weaken the discovery. If anything, it makes it feel more honest, more real, the kind of story where scientists are still standing in the middle of the mystery rather than looking back at it from a place of total certainty. Bertrand's team has continued modeling how this haze behaves as Pluto slowly moves through its extremely long orbit, which takes 248 years to complete just one trip around the Sun. As Pluto's distance from the Sun and its tilt shift over that long, slow cycle, the haze itself may shift with it, thickening in places, thinning in others, subtly reshaping the entire climate of a world most people assumed had no climate worth studying at all. The results were published on June 2nd in the scientific journal Nature Astronomy, laying out in careful technical detail how a haze so thin you could barely detect it with the naked eye turns out to be one of the primary forces steering the climate of an entire world. Think about the scale of that for a second. A layer of particles thinner than smoke, drifting hundreds of kilometers above a frozen, cratered landscape, quietly deciding how warm or cold an entire planet's atmosphere becomes, and quietly deciding how quickly that same atmosphere leaks away into the emptiness of space. And this does not just apply to Pluto. Scientists studying Saturn's giant moon Titan have long noticed a strikingly similar orange haze wrapped around that world too, hinting that this kind of haze-driven climate might not be some rare oddity, but a pattern that shows up again and again on small, cold worlds scattered across our solar system. There is an even stranger thread tucked inside all of this. Some researchers studying Pluto's haze chemistry have pointed out that early Earth, billions of years ago, before oxygen filled our atmosphere, likely had a thick, nitrogen-heavy sky full of similar hydrocarbon chemistry, closer in spirit to Pluto's atmosphere today than to the air you are breathing right now. That means a tiny, frozen world 5 billion kilometers away might be quietly holding clues about the very conditions that once existed on our own planet, back before life as we know it had even taken hold here. And here is where this stops being a story about one distant moon and one distant planet and starts being a story about us, about how the smallest, quietest things, a whisper of haze, a fingerprint of light, can end up rewriting how we understand where we came from. If the reveal in this story holds up under more study, then the next time anyone glances at a photo of a small, cold world anywhere in the solar system, the honest answer to whether it might have real, active weather changes from probably not to possibly yes. Share this video with the one person in your life who always says space is boring once you get past the big, colorful planets, because this is the exact story that proves them wrong. So what happens next? Scientists are not finished with Pluto, not even close. The James Webb Space Telescope is scheduled to continue observing Pluto and Charon across different points in Pluto's incredibly long 248-year orbit, watching how the haze thickens, thins, and shifts as the seasons on this distant world slowly change over decades. Because Pluto's orbit is so long, an entire human lifetime is not even enough time to watch it complete one full trip around the Sun. Scientists alive today are essentially handing this research down to the next generation, building a long-term record that future researchers, some of whom have not even been born yet, will eventually finish piecing together. Closer to home, this discovery is already reshaping how scientists think about atmospheres on other small, cold worlds, including icy moons around Jupiter and Saturn, and even small, distant objects scattered throughout the outer edges of our solar system that have never been visited by any spacecraft at all. If a world as small as Pluto, with gravity this weak, can hold on to a structured, layered, haze-driven atmosphere for billions of years, then other small worlds once dismissed as too tiny to matter may deserve a second, much closer look. Some scientists studying these outer worlds have also started asking a quieter, more unsettling question. If haze this thin can control the climate of an entire world, how many other small, cold places have astronomers already photographed, cataloged, and mentally filed away as boring, simply because nobody had yet pointed the right instrument at them for long enough to notice? That question alone is enough to keep entire research teams busy for years, combing back through old data from moons and distant icy bodies, looking for the same telltale infrared glow that gave Pluto's secret away. There is a very human thread running through all of this too. Every single person watching this video is, right now, standing on a planet with its own atmosphere, held in place by gravity, shaped by particles floating overhead, chemistry happening constantly above your head that you cannot see and almost never think about. The same basic physics that lets a whisper-thin haze steer the climate of a world 5 billion kilometers away is, in a smaller, different way, part of what shapes the weather over your own house tonight. Different scale, different chemistry, but the same underlying idea, that small, nearly invisible things can carry enormous influence. It is worth remembering that nobody on Earth can travel to Pluto and stand there to check any of this in person, not with any technology that exists today. Every single fact in this story arrived here as light, captured by delicate instruments, translated into numbers, and interpreted by patient researchers sitting in offices and labs scattered across our own planet, piecing together a picture of a world none of them will ever physically touch. That is, in its own way, one of the quietest kinds of magic tucked inside modern science. The idea that a world 5 billion kilometers away can still be understood in real, specific, testable detail, purely through the careful study of light that traveled for hours just to reach a mirror built here on Earth. Missions are already being discussed, informally, among planetary scientists, imagining what a future spacecraft built specifically to orbit Pluto, rather than simply fly past it once, the way New Horizons did in 2015, might discover if it could watch that haze evolve continuously, month after month, year after year, instead of catching just a single brief snapshot. No such mission has an official launch date yet. Realistically, if one were approved today, it would likely take a decade or more of planning, building, and a multi-year journey before it ever reached Pluto's distant neighborhood at all. Zhang, the researcher whose 8-year-old prediction started this entire chapter of the story, has said his team is continuing to refine their models, trying to nail down exactly how the size and shape of individual haze particles change the balance between the heating and cooling effects happening simultaneously in Pluto's thin, distant sky. That single detail, the precise size and shape of particles smaller than anything you could hold or see with your own eyes, may end up deciding whether future scientists conclude that Pluto's atmosphere is slowly stabilizing over time, or slowly, quietly, continuing to bleed away into space, one careful measurement at a time. By the time the James Webb Space Telescope completes its next full round of observations of the outer solar system, expected across the next several years, researchers hope to have enough data points spread across enough of Pluto's long orbit to finally build a real, working model of how its haze rises and falls with the seasons, rather than relying on a handful of scattered snapshots the way they have had to until now. Every additional data point tightens that model just a little further, the way adding more dots to a connect the dots puzzle slowly reveals a shape that was invisible with only a few dots in place. Every telescope observation, every published paper, every careful recalculation of how fast methane is escaping is really just one more small piece being added to a picture that will not be finished in any of our lifetimes. And that, honestly, is part of what makes it worth watching closely. Something is going to shift again, and probably sooner than most people expect. Somewhere right now, a researcher is quietly staring at a fresh batch of James Webb data, looking for the next small detail that does not quite match the model, the next thread that needs pulling. That is how nearly every major discovery in this story actually happened. Not with a sudden, dramatic reveal, but with one quiet, careful observation that slightly disagreed with what everyone expected, followed by someone patient enough to ask why. Pluto is still out there right now, in this exact moment, hundreds of times farther from the sun than Earth is, wrapped in that same thin, blue, quietly powerful haze, still leaking a little of its air toward Charon every single second, exactly as it has for billions of years, before any human ever looked up and wondered what was out there. Somewhere in the next few years, new data will arrive from that same telescope, and somewhere in that data, almost certainly, will be the next small detail nobody predicted, the next thread that unravels a little more of what we thought we understood about small, quiet, frozen worlds. Picture one single number, 1.3 kilograms of methane, escaping Pluto every second, forever, quietly drifting across the dark toward Charon's slowly reddening poles. That number, small and strange, has been running in the background since long before Earth had oceans, and it will keep running long after this video ends. Bookmark this video and come back to it once the next batch of Pluto data becomes public, because you will already understand exactly what you are looking at, instead of starting from zero the way most people will. Pluto did not ask the matter this much. It just kept quietly doing what it has always done, spinning slowly, wrapped in its strange blue mist, 5 billion kilometers from anyone who might notice. And now, thanks to one stubborn prediction and one very patient telescope, we finally have.